Let us now discuss a bit the methods of writing or pattern of writing a vector. Consider a vector A. How shall we write it in 1D, 2D and 3D? And the techniques should be very clear to you or known to you, and we shall also specify how we can move on to higher dimensions, starting from 1D, 2D, 3D to dimensions whose number is greater than 3. How to represent a vector in such a higher dimensional space. We can represent a vector A in 1D by writing Ax into x hat, or in other words, we can simply write vector A in this manner. In 2D space, this is for 1D, but in 2D we will have a similar thing repeated, and let us write it ay y hat, where y cap is perpendicular to x cap, and this can be written in coordinate form as ax ay. So in 1D one component, 2D two components needed to describe vector A. Now this way of writing means that we have used a row representation, row matrix representation. It is a row matrix representation, and we could as well write it in the form of a column matrix also, though usually this method of writing is popular and we'll use it at least now. In 3D we have to add another dimension, so we'll have another term like this. So the extension is easy, so the extra term that comes in is az z hat, where z cap is a unit vector that is perpendicular to both x cap and y cap, and we can write it using row matrix representation as ax ay az, and we can also write it using a column matrix. So this is the row matrix representation and this is the column matrix representation. Now what if we are asked to write the same vector in a dimension that is higher than 3, say in 20 dimensions or 100 dimensions? Now the method which we are following, if we still use that method in writing this vector in a 100 dimensional space, that will take a very long time. So the technique of writing should be changed. We should be clever enough to represent a vector A even in infinite dimensions. This is done simply by changing a notation, and now we'll focus on that. Actually, the notation here followed is not a friendly notation. It might seem to you to be easier because you have done it in the past, but actually this notation is very difficult, it is cumbersome, it is not a friendly notation. Now what will be an easier one? Easier notation is as follows. So alternate notation to represent vectors in any dimension. So this is vector A. In 1D, let us write it as A1 into I cap. Instead of I cap or X cap, let us use E1 cap. So then in 1D, vector A will be written as A1 into E1 cap. Now this notation is a friendly notation. This holds for 1D. Now if I ask to write the same vector A in a 2D format, obviously we will have another term added to this one, and that extra term will be A2 into E2 hat. In 3D, it will be A1 E1 cap plus A2 E2 cap plus A3 E3 cap. And if it is 1000 dimension, then the last term will be A1000 E1000 cap. So you can easily gauge how much friendly notation we have switched onto and how much complicated notation we were following when we were writing these things. So let us write it in an alternate way, a coordinate representation. So this is vector representation and this is coordinate representation. This is called vector representation because we are writing in terms of vectors. This is a vector representation, this is a vector representation, and coordinate representation is this one. This is called coordinate representation. So accordingly, this is a coordinate representation, this one is a coordinate representation because we are writing things in terms of coordinates. In 2D, therefore, it will be vector A equal to as mentioned, and in 3D, it will be and here we can write it as in coordinate representation A1 comma A2, and here we can write A1 comma A2 comma A3. Now let us try to write things in n dimensions. This will not be a problem because let us rewrite this one. So the first term will be A1 E1 cap, and then we have several terms, and then the last term will obviously be AN EN hat. Now here we can use the summation sign and write it in the following way. Summation over, say, alpha, this is A alpha E alpha cap, where alpha runs from 1 corresponding to the first term and the last term is n. So this is vector A. Here E alpha cap is the unit vector along the alphath direction. We'll make it still shorter, and to make it short we have to use a convention that was first proposed by Einstein, that was first used by Einstein, and is called Einstein's Summation Convention. Which says that one has to sum over repeated index. Now this index has a name. It is called dummy index or a run index. Let us illustrate. Here we are putting alpha equal to 1 to get this term, alpha equal to 2 to get the second term, and alpha equal to n to get the last term. Now alpha is the dummy index or run index. Because it assumes or it takes various values and it cannot be associated with a particular value. It just takes the values. So various numerics run over it. In n-dimensional space, we had written vector A as sum over alpha equal to 1 to n, and we wrote it as A alpha, E alpha hat. According to Einstein Summation Convention, this can be equivalently written as simply A alpha, E alpha hat, because the index that repeats is alpha. So if we write A alpha, E alpha hat, it is implied that we have to sum over alpha. Let us give another example. A square, let us write it in this way: a square equal to x square plus ay square plus az square. In 3D space, this is the square of the modulus of a vector A. Now if we change the notation, if we take 1 for x, if we take 2 for y, and if we write 3 for z, then a square can be written as a1 square plus a2 square plus a3 square, and therefore we can write in this way, which is an easier one, and this can be written simply as a alpha square. Here the index alpha is repeated because it is actually a alpha, and therefore if we write in this way, it is implied that you have to sum over alpha, and this leads to this expression. So what have we essentially learnt about Einstein Summation Convention? Number one, we can suppress the summation sign if we use Einstein's Summation Convention. And secondly, we have to sum over repeated index. And this is done to simplify things, so it is a very compact notation which we can use to our advantage. In 3D, we can write vector A as A alpha, E alpha hat, where alpha runs from 1 to 3, and in say 10D, vector A can be written as A alpha, E alpha cap. That is the same expression where alpha runs from 1 to 10 and so on. So this means generalization is possible, and we can deal with higher dimension easily. Now regarding higher dimension, you might have one or two questions which let me address. The first is how to deal with higher dimension. How to deal with higher dimension. Higher dimension is a complex thing and we can deal it effectively by using Einstein's Summation Convention and by a change of notation. So, change of notation, instead of x, y, z, we can use numbers, say 1, 2, 3 and so on. And another thing is use of Einstein's Summation Convention. That makes the problem look simple. Another question which crops up in one's mind is that, is such an extension feasible? Can it be done in reality? Let me mention a few points. We are not going into details, but simple points. The entire method of switching over from lower dimension to higher dimension, to be specific 2 dimensions greater than 3, is an abstraction. It's not a reality, it's an abstraction, and there is no harm to develop a theory. Another thing is that, let us be very clear that visualization is not possible. In other words, we cannot think of 4 axes set at right angles to each other, and therefore visualization is not possible. Let us note that we are 3D creatures, and to us 3 dimensions are meaningful and 3 axes can be set at 90 degrees mutually, and we cannot think of any other direction that makes 90 degree with all these 3 axes. So in that sense, we cannot visualize a 4 space or 4D. A creature who lives in a 1D world, say, cannot think of 2D, because the creature moves in 1D only, so it lives in a 1D universe and it cannot think of, or rather it has no concept of another axis or another dimension at right angles to it. Concept of another dimension or direction is absurd to it. In case of a 2D creature, it lives in a flat universe. The concept of height is meaningless for it. We are 3D creatures and we can think of 3 directions only which are perpendicular to each other, and to us placing another axis at right angles to them is simply meaningless. So we cannot visualize higher dimensions, but that does not mean we cannot develop a theory that involves dimensions which are greater than 3. It might be 4, 5, or it might be infinite dimensions. Someone might feel a bit awkward that we are supporting development of a theory on something, say a phenomena in higher dimension, that we can never visualize. First thing is that we cannot visualize does not mean that something, say a phenomena in higher dimension, does not exist or cannot exist. And another very important point is that at the beginning of the existence of universe, that is just after Big Bang, it is highly possible that higher dimensions did exist. So speaking about higher dimension actually opens up a huge possibility to explore and explain the universe in its baby stage. I will end this lecture after defining what we mean by rank. So what is rank of a physical quantity? This is a very important concept. Now the definition of rank is that it represents the number of directions which an observable has. So number of directions that an observable has is called rank, is called its rank. And let us denote rank by the letter small r. So this definition can be applied to scalars, and we mentioned that scalars are physical quantities or physical observables which have no direction. So scalars have no direction, and therefore scalars have rank 0. Vector. Vectors are observables or physical quantities which has one direction, and this means the rank of a vector is unity. So rank of a scalar is 0, rank of a vector is 1. So this is one way of defining rank. We can also note that there is another way to describe what we mean by rank. The number of indices and by indices we mean subscript plus superscript. That are needed to describe a physical quantity. Is called rank. In view of this remark, let us discuss a scalar. Now scalars need no index to be specified, and therefore its rank is 0. Let us explain this point. Suppose mass of a person is 50 kg. So we write m is 50 kg, and as you all know, we do not write it as mx, or writing it as my makes no sense. Temperature of a room T is 300 Kelvin. So this is how we write, and we do not write it as Tx or Ty or a component of a temperature, component of mass. These make no sense. So it is clear that we do not require any subscript or superscript to describe a scalar. Let me make another point clear. Let us consider x-axis. This is the unit vector along x, and let us consider a vector, say OP. So OP is a vector, and let us call it vector A, and sometimes we write it as ax x hat. Now what about this part? As mentioned in this lecture, this is a vector. Vector has two parts. One is unit vector, the other one is the scalar part. So this is the scalar part. Now this scalar part, even if we write in this way, that is, even if we attach an index or subscript to it, it is very clear that this subscript has no role. We can equivalently write it as ax hat by redefining ax as a. In other words, to express a scalar, we do not need any index. Even if you attach a subscript or a superscript, that does not give us any extra information regarding the scalar. Next, vector quantity. Now to express a vector, we need one index, and therefore vectors are of rank 1. Consider a vector A, and in 1D we can write it as ax x hat. In 2D we can write it as ax x hat plus ay y hat, and in 3D we will have another term component wise. We can write it as ax to express a vector. It is very clear that we require one index, and here that index is a subscript. Here ax in 1D, ax ay in 2D, ax ay az in 3D. So the main point is how many indices we require. We require one index if it is a 1D vector. We require one index if it is a 2D vector. We again require one index here if it is a 3D vector. So whatever be the dimension, if it is a vector, we need one index for its expression, and therefore the rank of a vector is 1. How many components do an observable have in d-dimensional space? And the answer is d to the power r, where d is the dimension and r is the rank of the physical quantity or observable under consideration. Let us consider a scalar quantity. In d-dimensional space, how many components will it have? Now scalars are characterized by the fact that they have rank 0. So the number of components is d to the power r, so it is d to the power 0, and d to the power 0 is 1. So scalars have one component in all dimensions, in any dimension. So irrespective of the dimensionality of space, a scalar will have only one component. Now what about a vector? As already specified earlier, to express a vector we require d components. Now let us check. The general formula is number of components which an observable has in a d-dimensional space is d to the power r, where r is the rank of the observable. So a vector will have d to the power r, and r is 1 number of components. So d to the power 1, that is d components. So scalars in any dimension will have one component, but a vector in d dimensions will have d components. And let us recheck it in 1D, in 2D, in 3D. In 1D, a vector A will have one component, and that is Ax. In 2D, it will have two components, Ax and Ay, but in 3D, it will have three components, Ax, Ay and Az. One component, two components, three components, so d components in general in a d-dimensional space. Let me end here with a mention of the fact that rank represents number of directions which an observable has, scalars which has no direction, and therefore its rank is 0, and in any dimension it will have one component. Vectors are quantities which have one direction, and therefore its rank is 1, and in d-dimensional space it has d component.